Conservation laws are very important in physics. Applying the force concepts developed in dynamics, energy conservation and momentum conservation can be derived. This presentation discusses these two important conservation laws of point mechanics. The photo illustrates one important aspect of energy conservation in mechanics, namely the conversion of potential energy into kinetic energy and then possibly back into potential energy. On this roller coaster shown, the conservative weight force performs work on the moving inertial mass of the cars that results in fast motion on the way down. Work is a new quantity that needs to be defined in order to introduce energy into mechanics. Applying a force to an object to an inertial mass can result in work being performed. However, the character of this force determines if this work is reversible or not. Certain type of forces, namely conservative forces, permit such a reversion. In contrast, non-conservative dissipative forces do not allow that. In the case of this roller coaster, if friction and drag are neglected, the kinetic energy of the motion is converted back to gravitational potential energy on the way up. Our experience tells us that applying a force is typically associated with a certain effort. We know that in line with the first law of the inertia principle, moving a box on slippery ground takes no effort. This is because in this situation, the object is in continuous motion at constant speed, and in fact no force is applied at all. This type of motion requires no effort. In contrast, moving the same box on rough ground with considerable friction between the surface of the box and the ground requires considerable effort. In this case, our force push has to overcome the friction force that acts in the opposite direction we are pushing in. The effort associated with this push force depends also on the distance that we want to move the box. If it's just a short distance, the effort is reasonable. However, if the distance is long, more and more effort is required to move the box over this distance. The situation is somewhat similar if we move a box against a spring. This also takes considerable effort. The effort depends on the magnitude of the force and the distance by which the spring is compressed. Can this effort that we're experiencing be quantified? Is there a difference between the effort afforded against friction and that afforded against the spring? In physics, the effort in applying forces is quantified using the concept of work. Work is defined as an integral over the scalar product of force acting in the direction of displacement. F vector times dr vector. The dimension of work is therefore 1 Newton meter. Because of its importance, this unit has also been given a specific name, 1 joule. 1 Newton meter equals 1 joule. Since force and displacement are multiplied using the scalar product of vector algebra, work is a scalar. It does not have a directional quality and depends on the magnitude of the force and the length of the displacement, dr. The magnitude of work also depends on the relative direction of the force vector and the dr vector. Only the component of the force vector that is parallel to the direction of the displacement vector is considered in the calculation of the work performed on an inertial mass when it is moved by this displacement dr. In one dimension and for a constant force, the integral simplifies simply to work equals force times delta x, where delta x is the distance over which the inertial mass has been moved by the force F. Notice that this quantity of work is defined positive. This sign convention is not unique in physics. In some disciplines or textbooks, this type of work is seen as a negative quantity. Although the one-dimensional version of the force integral F times delta x does not involve the scalar product, the relative sign of force and displacement delta x still matter. If the force x in the opposite direction as the displacement delta x, the work is negative. If force acts in the same direction as displacement, the work is positive. A full appreciation of the work integral requires an understanding of the mathematical scalar product of vector algebra. The scalar product combines two vectors to yield a scalar by taking into account the angle between these two vectors. That's illustrated here at the top left. The force vector points at 1 o'clock and the dr vector is in the horizontal, so they are separated by an angle theta. Multiplying these two vectors with each other using the scalar product is equivalent to projecting a component of the force onto the direction of the displacement dr. The magnitude of this force component and the magnitude of the displacement vector dr are then multiplied. The scalar product f vector times dr vector is therefore equal to f magnitude times dr magnitude times the cosine of the angle theta between the two vectors. This means in particular that the scalar product is positive if the two vectors f and dr are parallel, and that it is negative if these two vectors are antiparallel, because the product involves the cosine of theta, and antiparallel is equivalent to a theta of 180 degrees. The cosine of 180 degrees is -1. For every situation in between, the cosine of theta modifies the product f dr. Since work is an integral of force integrated over the displacement dr, work can be visualized in a force versus displacement diagram. In fact, it is equal to the area under the curve that represents the force in this diagram. This is shown for a force that acts on an inertial mass with a respective angle of theta in the top right diagram. In this case, the force is constant, and the fact that it is not aligned with the displacement is taken into account by multiplying the magnitude of the force F with cosine theta. This gives a constant line in the diagram. The work associated with this force, which moves the mass from the left to the right over a distance d, is equal to F cosine theta times d, which is the shaded area under the red line. In the diagram underneath, a situation is shown where the force increases linearly with displacement d. This could, for example, be the force acting against a spring, compressing a spring. As before, the direction of the force and the direction of the displacement are not aligned. Therefore, the cosine theta comes into play. The integration of the area underneath the curve is shown in discrete steps. The sum of those 6 discrete areas approximates the work performed when moving an inertial mass over the indicated distance. When making the distance di infinitesimally small, this sum of discrete areas becomes the integration of the curve. Work is the integral of the scalar product of force and displacement. This view graph shows that applying the second law to the new concept of work leads to a definition of kinetic energy. For clarity, this is all shown in one dimension, however the derivation in 3 dimensions is equivalent. Assuming that a force F moves an inertial mass from a position xi to a position xf, the work associated with this applied force is the integral from xi to xf over f dx. Since Newton's second law F equals ma is always applicable, we might substitute for F with ma. Using kinematics to represent the acceleration a as the time differentiation of v, dv dt, we can reinterpret this integral. Substituting for the differential dx with the differential dv, this shows that this integral is equal to an integral from the initial velocity to the final velocity over the product mv. Carrying out this integration, we obtain work equals 1/2 mv final squared minus 1/2 mvi squared, where m is the inertial mass that has been moved. Work is just equal to a change of a quantity 1/2 m velocity squared. This quantity 1/2 inertial mass velocity squared, we call kinetic energy. Kinetic energy has the same dimension as work. It is therefore also measured in Newton meter or joule. It is appropriately named kinetic energy because it involves the velocity v. The force variable in the work integral can be substituted with other specific forces. This view graph shows the situation for the weight force mg. The weight force mg performs work on a mass, as shown at the bottom left, that drops from a height h to the ground. Equivalently, lifting this box from the ground up to a height h requires work because a force has to overcome the opposing weight force. The work integral for these displacements is therefore integration from an initial position yi to a final position yf over the force mg integrated over the displacement dy. This is equal to mg times yf minus yi. As before, we see that this integral represents a change of a quantity that is equal to mass times acceleration due to gravity and height y. We call this new quantity u equals mgy, the potential energy associated with the weight force. Lifting the box over a certain height h requires work to be performed that transfers this work as potential energy to the box. As with work and kinetic energy, the potential energy is measured in units of Newton meter or joule. Applying the definition of work to a force that performs work on a mass acting against a spring force F equals minus kx, we obtain a very similar result. In this case, the integration also starts at position xi and finishes at position xf, and the integrand is equal to k times x. Carrying out this integration, we obtain the difference 1/2 k x final squared minus 1/2 k x initial squared. We interpret this difference as the difference of a quantity 1/2 kx squared, which we call the elastic potential energy, the potential energy of the spring. With both of these forces, weight force and spring force, the work performed against these forces, F times dx, by lifting a box up to a height h or by compressing the spring, is equal to the work that these forces themselves, the weight force and the spring force, perform on the mass when it returns to its original position. For example, in the case of the weight force, work is converted to potential energy, U equals mgh, and when the box then drops again, this potential energy via different work, but of the same magnitude, is converted to kinetic energy 1/2 mv squared. All these energies are of the same magnitude. We notice that energy is conserved. It cannot be overemphasized that energy conservation is one of the most important laws of physics. We conclude that in a mechanical system, the sum of kinetic energy and potential energy, which is equal to the total mechanical energy, this sum remains constant if the forces are conservative. This sum is conserved. Mathematically, we write for a point mass under gravity, Ki plus Ui equals Kf plus Uf. The initial sum of kinetic and potential energy equals the final sum of kinetic and potential energy. Written out, we can write 1/2 mvi squared plus mgyi equals 1/2 mvf squared plus mgyf. Equivalently, for a point mass on a spring, we can write 1/2 mvi squared, the kinetic energy of the point mass, plus 1/2 kxi squared. Xi is the position of the spring, the initial position. That sum equals 1/2 mvf final squared plus 1/2 kxf squared. K, of course, is the spring constant. This energy balance is particularly useful in the description of oscillations of springs. Apart from being of fundamental importance, the conservation of energy also provides for a powerful tool in problem solving that often is an alternative to the approach using dynamics and Newton's laws. In relation to the previous slide, energy conservation was specifically ascribed to conservative forces. The question arises, what are conservative and therefore what are non-conservative forces? Here we are looking at two examples. The friction force is not conservative. In contrast, the spring force is conservative. Both forces oppose the external push force. So what is the difference? In the case of friction, the work performed by the external force on the mass m is converted to heat and noise. These energy forms are outside mechanics. We also say that the mechanical work is dissipated into external energy forms. This external energy cannot be converted back to mechanical energy. In contrast, the work performed against a spring is converted into the potential energy of the spring. This is a mechanical potential energy. This potential energy can be returned to the mass m, and in this sense it can be regained. The return occurs when the compressed spring expands and pushes the mass m to the left. We conclude that dissipative forces cause a loss of mechanical energy into other energy forms. These other energy forms are often called internal energy, and typically they are heat or sound. The loss into internal energy reduces the available mechanical energy and causes a change, delta E mechanical, which is equal to minus the work performed by the dissipative forces. For example, in the case of friction, this work is minus the friction force times d. Here d replaces the displacement of the mass m, and the minus sign indicates that the friction force opposes this displacement. The arguments are equivalent for the three-dimensional situation, which however has been skipped here for clarity. This demonstration experiment shows the effects of dissipative forces. A 1 kilogram weight is dropped onto a blue styrofoam pad. The kinetic energy of the dropping weight is converted to heat on impact. The impact leaves two marks, and the image from an infrared camera shown on the right indicates that at those marks the temperature increases by several degrees. The average temperature of the pad is about 22.8 degrees Celsius, and at the marks the temperature is possibly as high as 26 degrees Celsius. This different demonstration shows the conversion of mechanical work to heat as an internal energy form. A thermometer and an accelerometer are dropped into a container and read out remotely. A considerable amount of sand is added, and the container is vigorously shaken. The reading of the accelerometer shows the acceleration of the sand inside, therefore work is performed. In parallel, the thermometer shows an increase in temperature, confirming that the work has been converted to heat. The law of energy conservation is one of two conservation laws in mechanics. The other one is momentum conservation. Momentum conservation is a consequence of Newton's third postulated law. This is illustrated here with a vector diagram on the left. At a point in time, t, 2 point masses, m1 and m2, move with their respective velocities as shown. The 2 point masses interact via the third law pair. Therefore we can write F of 1 on 2 is equal to minus F of 2 on 1. One may, for example, think of a gravitational attraction between the two. Rearranging gives the sum F12 plus F21 equals 0. Using the second law of Newton, this can be written as m1a1 vector plus m2a2 vector equals 0. Thinking this through further, one can now apply the equations of motions of kinematics, because acceleration is the first time differential of velocity. So m1 dv1 on dt plus m2 dv2 on dt equals 0. Applying the product rule of differentiation and taking into account that the point masses are constant, we find that we get two differentiations that add up to 0. m1 v1 differentiated with respect to time plus m2 v2 differentiated with respect to time equals 0. Since the product of mass and velocity is momentum, we can also write this as d on dt of p1 plus d on dt of p2 equals 0. In the last step, integrating both sides with respect to time, we find that the sum of the two momenta p1 and p2 has to be constant. And for dimensional reasons, we can define this constant as the total momentum p total. It is important to recognize that this procedure is independent of time, therefore p total is constant with time, and also, because we can always apply the principle of linear superposition, this procedure can be applied to more than two masses. Furthermore, the type of interaction between the 2 point masses is irrelevant, because Newton's third law, action equals reaction, always applies. We therefore conclude that the total momentum of a system, that might be 2 point masses, or 3 or 4 or many more point masses, the total momentum of a system of point masses is always conserved. The momentum, mass times velocity v, is a vector. It is therefore important to realize that the total momentum, that is also a vector, the total momentum of a system of particles is conserved in both its magnitude and in its direction. This may be emphasized by writing the two momenta in their component notation. The vector comprising the x, y, and z component of momentum 1 plus the vector comprising the x, y, and z component of momentum 2 equals the total momentum vector. We note in particular that this gives us three independent equations. Therefore, in 3 dimensions, combining the law of energy conservation and the law of momentum conservation typically gives a system of 4 equations. Such 4 equations can be a powerful tool in problem solving. Since the total momentum vector is associated with the combined mass and acts at a certain point, it has to be clarified where this point is in space. As with any point mass, the momentum vector is placed at the center of mass of this system of particles. That's illustrated here in this sketch. For 2 point masses, the center of mass of the system of these 2 particles is on the line that passes through both of these point masses. If those masses are equal, as shown in the sketch, then the center of mass will be right in the middle between them. The total momentum vector p total is the vector sum of the 2 contributing momentum vector. That is shown by the dashed vectors that are translated to the position of the center of mass and added together vectorially. The center of mass of the system moves with the total momentum p total. The law of momentum conservation is particularly relevant to collisions between 2 particles. We distinguish 2 types of collisions: elastic collisions and inelastic collisions. Both types of collisions are illustrated here in 1 dimension. The situation in 3 dimensions is equivalent but has been omitted here for clarity. In an elastic collision, the 2 point masses collide and separate again. In an inelastic collision, the 2 point masses collide and stick together. The combined mass of these 2 particles is then represented by the new center of mass. For elastic collisions, it can be shown, using both the laws of momentum and energy conservation, that the velocities before and after the collision are given by the 2 equations shown at the top. Similarly, as shown by the equation at the bottom, in an inelastic collision, the momentum after the collision of the combined system, m1 plus m2 times the final velocity, is given by the sum of the momenta of the point masses before the inelastic collision. The superscripts here refer to I for initial and F for final. A classical demonstration of momentum conservation of elastic collisions in 1 dimension is Newton's cradle. In a Newton cradle, as the one shown here, several metal balls undergo elastic collisions. interesting patterns can be created. The symmetry of the pattern comes about because momentum is conserved. For example, if one ball collides with the others, then the momentum is passed to the last ball on the other side in a series of elastic collisions. Then this is repeated in the other direction. If two balls are lifted and collide with the remaining balls, the initial momentum is twice as large, and on the other side two balls will move. Furthermore, if on either side a ball is lifted to the same height, then the total momentum, the net momentum, is zero, and this is maintained throughout the collisions. The net momentum is zero because the momentum vectors associated with the balls on either side cancel each other, since those vectors point in opposite directions and they are of the same magnitude. The same happens when two balls on either side are lifted to the same height and collide with each other. The momentum vector associated with two balls is twice as large, but again, the vector on the left compensates the vector on the right because the directions are different by 180 degrees. Since the steel balls have hard surfaces, very little kinetic energy is dissipated into heat or sound. This is why the collisions are elastic and why the motion is maintained for a relatively long time. Momentum conservation is also inherent to billiards, as demonstrated here. It is also most readily illustrated with coins. Momentum conservation is true in 1, 2, or 3 dimensions. This example illustrates the situation in 2 dimensions. A point mass m1 collides with a point mass m2 as shown in the sketch at the top left. For clarity, it is assumed that both masses m1, m2 are the same and equal the mass m. The two momenta of the masses before the collision are shown in the vector diagram in the center of the view graph. The two momentum vectors are both drawn from the origin. Adding the two vectors together gives the total momentum vector as shown. In this case, point mass 1 has a momentum with an x component 2 and a y component 1, and momentum 2 has an x component of -1 and a y component of -2 in units of kilograms times meters per second. Adding this together gives the momentum vector for the total momentum, p total, as 1, -1. The x component is 1 and the y component is -1 in units of kilogram meters on second. In order to keep this example simple, it has been assumed that the mass m equals 1 kilogram. Since momentum is conserved, the sum of the two final momenta, p final 1 and p final 2, has to be equal to this total momentum 1 minus 1 kilogram meters on second. This is only possible if the final momentum vector of point mass 1 is equal to -1 minus 2, and the final momentum vector of point mass 2 equals 2, 1. We see that in this elastic collision, the two masses swap their momentum vectors. The speeds of both masses remain the same, but each mass has now a different direction of motion, as given by the respective final momentum vector. Applying Newton's second law to the work integral, it can be shown that in mechanical systems involving only conservative forces, energy is conserved. Similarly, starting with Newton's third law, it can be shown that momentum is conserved. In 3 dimensions, 4 equations are obtained. The sum ki plus ui equals the sum kf plus uf. The sum of kinetic and potential energy at an initial point in time equals the sum of kinetic and potential energy at a point in time later, a final point in time. In addition to this equation, 3 further equations are obtained because the sums of the 3 components of the momentum vectors are individually conserved. The sum of vector p1 plus vector p2 is constant and is equal to the total momentum vector p, which is conserved. These equations can greatly simplify the solution of problems, in particular since they often provide for an alternative to approaching problems using Newton's laws. This presentation of point mass mechanics started with a discussion of the foundations of physics and mechanics. This was followed by a discussion of kinematics and a description of dynamics culminating in Newton's three postulated laws. We concluded with a discussion of conservation laws, in particular the laws of momentum and energy conservation. In regard to the foundations of physics and mechanics, we may want to summarize the following 5 points. The strength of physics arises from the interplay of theoretical modeling and experimental measurement. Concentrating the mass of an object at its center as a point mass has turned out to be a powerful abstract reduction. This reduction permits point mass mechanics. Point mass mechanics requires calculus, vector algebra, and dimensional analysis as important theoretical tools. Experimentation, as introduced by Galilei, is enabled by three fundamental quantities, namely time, length, and mass, and also a system of units. Typically, the SI system is used. Important aspects of measurement and experimentation are standards, experimental uncertainties, the propagation of such uncertainties, and the quotation of results to significant figures. In connection to dynamics and kinematics, we found that Newton's three postulated laws form a correct and complete foundation of point mass mechanics that is valid without any amendments in inertial reference frames. In non-inertial reference frames, fictitious pseudo-forces, such as for example the centrifugal force, can provide for necessary amendments to Newton's laws. The second law by Newton makes clear that any net force, different from zero, acting on an inertial mass causes the acceleration of this mass. The acceleration is therefore the consequence of this net force. Once the acceleration of a point mass is known, the equations of motion of kinematics can be used to also determine the position and velocity functions of time, and consequently the trajectory of the inertial mass can be established. The third law by Newton assures us that every force has an anti-equal partner force, and that these two forces form a symmetric force pair, with each force acting on different objects. The first law tells us that in the absence of any net force on a point mass, an inertial frame of reference exists in which this mass is in a static equilibrium and at rest. We began our discussion of conservation laws by quantifying the experience of an effort of applying a force to an object by using the concept of work. Combining the second law and this definition of work, the energy forms kinetic and potential can be introduced. We found that in mechanical systems with only conservative forces, the sum of kinetic and potential energy is conserved with time. Dissipative, non-conservative forces reduce the total mechanical energy available to the system. Using the third law by Newton, it can be shown that momentum is conserved with time in the interaction of two or more point masses. Combining energy and momentum conservation is typically a powerful tool in problem solving. However, what about the feather and the hammer? We started our discussion by looking at this classic example of the drop under gravity of a feather and a hammer. Apollo astronauts showed that on the Moon, in effective vacuum, both hammer and feather fall the same. Aristotle disputed this. According to Aristotle, the much more massive hammer will fall faster than the less massive feather. How does classical point mass mechanics explain the fall of these objects? Let us first look at the situation in vacuum. As with any problem in point mass mechanics, we can confidently start with the second law. The consequence is the free fall. There is an acceleration. There must be a cause. What is the force that causes the acceleration? It is the weight force mg, and we write mg equals ma. Since the masses cancel, we see that for both the hammer and the feather, the acceleration a is equal to g, and g is constant. Therefore, in vacuum, hammer and feather will hit the ground at the same time. They experience the same acceleration. If we want to, we can work out the velocity of both objects using the equations of motion of kinematics, because a equals the first time differentiation of velocity v, and therefore v is the integration over a with respect to time. V becomes a times t. The Apollo astronauts demonstrated the equal fall of feather and hammer in vacuum on the Moon, which has lower gravity than Earth and no atmosphere. Since on this mission the landing module was called Falcon, a falcon feather was used and a geological hammer. Both fall somewhat slower than in a vacuum on Earth, however they fall with the same velocity and impact the ground at the same time. Let us now look at the situation of the feather in air. Again we start with the second law. What is the cause in this case? What forces contribute to the consequence, namely the acceleration a? We identify two forces. The weight force mg pulls the inertial mass of the feather downward. However, this force is opposed by a drag force, which we can approximate using minus drag constant times velocity. So the sum of forces is mg minus bv. Because of the second law, that's equal to ma. If we rearrange, we find that the acceleration in this case is given by the constant g minus b on m, which is also constant, times the changing velocity. Initially, the velocity is effectively zero, and the motion is therefore the same as in vacuum. However, very quickly the velocity increases, since both mass and drag are constant and positive parameters, so therefore the acceleration decreases, and eventually we find that b on m times v is approximately the same as g. Therefore, at this point, the acceleration is effectively zero, and the first law by Newton tells us that now we have a constant velocity, which we call v terminal velocity, and it is given by the ratio of mg on the constant b. We see that in contrast to vacuum, where the feather is all the time in uniformly accelerated motion, in air the feather very quickly adopts a uniform motion with a constant velocity. This experiment compares the fall of a feather and two steel spheres. It is set up in a vacuum chamber, however, this initial experiment is in air. Clearly, the feather falls much slower than the steel balls. Here we see the same arrangement and drop with the air pumped out. Feather and steel balls fall equally fast. The same considerations just discussed for the feather in air also apply to the hammer in air. We start with the second law, and we derive, considering both the weight force and the drag force minus bv, we derive that after some time the hammer will undergo uniform motion with the constant terminal velocity given by mg on b. So the question arises, why does the hammer hit the ground first? Well, the reason is that the mass of the hammer is much larger than the mass of the feather, and the drag constant of the hammer, because of its shape, is much smaller than the drag constant of the feather. Therefore, the ratio m on g for the hammer is large, and the ratio m on g for the feather is rather small. The terminal velocity of the hammer is much larger than the terminal velocity of the feather. According to kinematics, this means the hammer will hit the ground first. We can see that in contrast to Aristotle's speculation, Newton's point mechanics describes the difference between the fall of a hammer and that of a feather in a correct and complete fashion. A typical problem in point mass mechanics involves one, sometimes two masses. The principle of linear superposition permits the extension of the principles and conclusions of point mass mechanics to many particle systems. If the number of particles is large, such a many particle system approximates a rigid body. A rigid body has a finite extent, and in addition to linear motion, it may also rotate. The physics of rigid bodies, including their rotation, is described in rigid body mechanics.